Hello, I'm Colin from We Learn to Share, and today's lecture is about gases. To begin this chapter, let's talk about the measurements of gases. Volume, amount, temperature, and pressure are used to describe a gas in a complete way. The first three quantities were described in previous lectures, so I'll just explain some significant features. The volume of gases is equal to the volume of the container since it expands uniformly to fill the container it is placed in. The amount of gaseous samples are commonly expressed in the number of moles, which we discussed in Chapter 3. The temperatures of gas in calculations involving its physical behavior must be expressed on the Kelvin scale. Now, let's take focus on the last quantity, pressure. Pressure is defined as force per unit area, and the pressure of gas is the amount of force the gas exerts on the unit area of its container. There are two devices which can be used in the method of measuring pressure. Atmospheric pressure can be measured using the barometer. The pressure of the atmosphere is represented with the height of the column. The pressure of confined gases can be measured with the manometer, and this method measures the pressure relative to the atmospheric pressure. Most barometers and manometers contain mercury for their liquid because its high density allows the devices to occupy less volume. The pressure measured in these methods can be expressed in these units: millimeters of mercury, Pascal, bar, and atmosphere. The conversion factors between them are likely to be shown in problems, but it will be convenient to memorize them. Gases resemble each other in the relationship of the quantities we just discussed about. First, volume is directly proportional to the amount. Second, volume is directly proportional to temperature, absolute temperature in kelvins, according to Charles and Gay-Lussac's law. Third, volume is inversely proportional to the pressure of the gas, according to Boyle's law. These three characteristics form the ideal gas law, which can be expressed as this equation. Here, the capitalized alphabet R is the gas constant, and it can be calculated by substitution of the experimental values of P, V, and T. The ideal gas law is used in the textbook to solve problems such as problems relating to the final and initial states of gases and the calculation problems of P, V, and T, molar mass, and density when the other values of the equation are given. However, this equation does not work for other physical states, and it is important to note that the ideal gas law equation can be used only for reactions involving gaseous reactants and products. It is possible to apply stoichiometry to gases too. The first stoichiometric relationship discovered was proposed by Gay-Lussac, who we talked about, in 1808. It was the law of combining volumes. The law states that the volume ratio of two gases in a reaction is same as the reactant mole ratio, of course at constant temperature and pressure. We can see that the law can be explained by the ideal gas law since volume is directly proportional to amount, or the number of moles. The ideal gas law can also be applied to gas mixtures. This relation on below is Dalton's law of partial pressures. The quantities above showing nART divided by V and nBRT divided by V are the pressures that gases A and B would exert if they were alone, and they are called the partial pressures. The total pressure is the sum of partial pressures of the gas components. The partial pressure of water vapor is equal to the vapor pressure of liquid water, and its value is fixed at a given temperature. The vapor pressure of water can be used in the calculation of the partial pressure of the gas making up the mixture with it. The ratio of Na to N total is the mole fraction of substance A in the total mixture, and the partial pressure of a gas A in the mixture can be calculated by multiplying the fraction to the total pressure. Here, we can get to another concept, the kinetic theory of gases. It is based on the idea of the similar behavior of gases when motion is concerned. To explain this, we start with a simple molecular model regarding these properties of gases. First, the total volume of the molecules is negligibly small compared to the volume of the container, since gases mostly consist of empty space. Second, gas molecules are in constant chaotic motions and collide frequently with one another and the container walls, so that their velocities change constantly. Third, all collisions between molecules and the collision between molecules and the container walls are considered elastic. Fourth, pressure is generated by the collision between molecules and the walls of the container, so pressure increases as the energy and frequency of collisions increase. Applying the laws of physics to this model, we can calculate the pressure of gas like this equation, where U is the average speed of molecules. The ratio N divided to V expresses the concentration of the molecule, so as it increases, the collision frequency increases and the pressure increases. The other term, mass times U squared, will look quite familiar if you've studied physics. It represents the energy of collision. The rate of effusion is directly proportional to the average speed and to the pressure of gases. Effusion is similar to diffusion, but it is easier to analyze since it's done at low pressures through tiny pores or pinholes. We can also derive this equation through mathematical calculations. The equation is called Graham's law, and it states that at a given temperature and pressure, the rate of effusion of a gas is inversely proportional to the square root of a smaller mass. Let's take a short look on the Maxwell distribution before we end the class. In 1860, Maxwell showed that different possible speeds are distributed among particles in a definite way, and developed a mathematical expression for these. In this distribution curve for these molecules, we can see that as temperature increases, the speed of the molecules increases, and the curve becomes broader. So it is possible to assume that the chances of molecules having faster speed increases as temperature gets higher. However, the gas laws we have learned about do not accurately match the gases of real life, and they deviate from the ideal gas law as they get closer to the liquid state. This is the end of today's lecture. Next time, I'll continue my course onto Chapter 6, so don't forget to subscribe to the channel, turn on the notifications, and leave a like.